Alright, I'm going to do a quick kit build here. It's not a very complicated kit, so hopefully I can do it pretty quickly. This is called the 1802 badge. It's one in a series of name badges designed by Lee Hart with the help of the other gentleman here. It was released on the 5th of September 2024, and these are made for the Vintage Computer Festival Midwest. They don't come out every year, but every 2 or 3 years it seems like there's another one, each based on a different microprocessor from the past. And with this one being an 1802, you know it's going to be a clever circuit, because Lee can't help but make clever circuits out of 1802s. What is it? A cool retro name tag that displays a scrolling message of your choice. Celebrates the 50th anniversary of the introduction of the microprocessor. Classic user interface that is functional and educational. Minimal size, cost, and parts count. Maximum fun. It is a complete working 1802 computer built entirely with vintage parts and technology. Powered by batteries or a USB port, its LEDs display up to a 32-character scrolling alphanumeric message. Onboard buttons let you set the message directly, or a serial port provides user interaction with any computer. It has an 1802 microprocessor running at 2 MHz, an optional 8K RAM with battery backup, an 8K EPROM expandable up to 32K, an 8-digit 14-segment starburst LED display, software-driven 9600 baud TTL serial I/O port, and just a few components to tie it together. Now, this video is going to have music in the background and lots of noise because yesterday a large crew came to de-roof my house. It's an old house, and for many years I was growing uneasy about the condition of the roof, not shingles, but yes, and it had a couple of leaks, but they couldn't really be addressed until the underlying issues were dealt with, and that was pretty substantial structural issues, wood rot, and so on. So I decided to bite the bullet and hired a contractor to come out and hire the appropriate subcontractors, and they've been busily at work. Yesterday the old roof came off and a lot of work got done on the framing, new rafters, and lots of other wood replacement, and as of now the roof is back on shingled and everything, and they're doing things like installing the chimney, and the fascia and soffit guys are out doing that. They found a couple of badly rotted boards which they had to send out to get new lumber from the lumber yard before they can continue. And once they've got that done, then as soon as the supplier has some more in stock, my new siding will be installed, so it's going to look like a very new house. Anyway, that's just by way of excuse for all the noise, because right above the ceiling here a bunch of guys are clomping around, and the guys are sitting out on a scaffold just outside the window. So anyway, so I'm going to do this build here. There are all the parts. A USB to RS-232 type interface board, connector for that, a lanyard clip for the name badge functionality, both of the display modules, ICs in tubes, diodes. I believe this is a ceramic resonator, or yeah, that's probably what it is. A switch, that's power switch probably. A bit of hardware, 3 tactile push button switches, various ceramic capacitors, a couple of resistor networks, and a discrete resistor, pack of batteries included, and a battery holder, and of course the circuit board. Happy 50th birthday, vintage microcontrollers. So holes for the display, holes for a couple ICs, holes for the microprocessor, more holes. I believe that's RAM and EPROM, one on top of the other. And this is probably the front, because there's more text on it. Nice tight layout. Lee's really good at that kind of thing. So I went through the parts list and found that just a small error, that it says quantity of 1 LED and there's actually 2, and there is no socket included for the EPROM, even though there should be according to this, and it's using a socket strip rather than a regular socket, because the way Lee often does his circuit boards, there's a particular RAM IC. There's the air compressor in my basement's going to start. Yep, there it goes. The way Lee likes to do these is there's a particular RAM chip which has this configuration. It's a 0.3 inch spacing, so the 2 inner rows of pins there, and it fits underneath an EPROM with the same number of pins but at a 0.6 inch spacing, and a lot of the pins line up. Some of them do, some of them don't, but it's fairly convenient to put one under the other one. And if you get a 32K EPROM and a 32K RAM chip, you can fit 64K of RAM into that little tiny area. Anyway, he confirmed by email that in this design, currently, the RAM does nothing. This is essentially a RAM-less design to do what it's supposed to do. Therefore, he recommended not installing the RAM at all, or making provisions for it, because they don't have any real plans to develop the design to the point where it would use the RAM. Although individuals could do that. An individual who wants to turn this into a full-fledged 1802 based microcomputer, which it could be, could decide that they want to have all the RAM and ROM possible on it. But as the name badge, it does use EPROM. It does run a program in EPROM, but it uses no RAM to do that, which seems incredible. But the 1802 has a lot of 16-bit registers inside of it, and by clever program writing, you can get away with just using those as RAM, even though they're being used primarily for storage of the digit data for the message you want to display. But you can still be clever with the software, and it's very minimal software, I believe, that is in here. It doesn't need very much of a program to do the message display function. So somebody's made a very clever program that just does not use any external RAM. So that's the way I'm going to do it. I don't plan to use this for anything except the name badge function, so I'm going to forego that. But I do plan to put the other ICs in sockets, and the 1802 in a socket, and probably the EPROM in a socket, because I might want to change it out with a newer revision if one comes available. Well, just looking through my parts bins, I did find an IC socket that's appropriate for the EPROM, has the right number of pins in the machined terminal style that I like. I found a very low profile socket for the 1802. That'll work. If I can get it back out of the board. And I found a couple of whatever these are, 1, 2, 3, 4, 5, 6, 7, 8, 20 pin 0.3 inch dip ICs, which can be used up in these locations for those two. So I have everything that I want to socket already here. I had placed an order with DigiKey yesterday for the parts I would need if I was going to do it the way the instructions suggest, but since I'm not going to put the RAM in, I don't need to do that, and the displays are not socketed. It's important to make sure the board is oriented correctly, because it does have writing on both sides of the board that's silk screened, and it's the side with all the IC identifiers. That's the front. You don't want to start assembling components to the back side of the board. Alright, the IC sockets are on the board. Alright, all the capacitors are soldered on. 3 diodes and 1 axial leaded resistor. And the 2 resistor networks, those are those 2 vertical oriented black things either side of the microprocessor socket. The power switch is over there on the left side of the board now. Little slide switch. And the ceramic resonator, that little light blue thing, is on there now. And the displays are soldered on. Alright, I've mounted the 2 so-called jack screws. They're just male-female spacers, really, with flathead screws put into them on this side, and then the nuts on the back side of the board underneath the 1802 socket. And I think this is a mistake in the bill of materials and the instructions, because with the nuts here, even if you didn't use a socket, the 1802 would try to be sitting up on top of those, and if they ever came loose, you wouldn't be able to tighten them. So yeah. And the 3 push buttons are installed. The battery holder has this sort of exposed wire going diagonally through a shallow channel, and since this is going to get mounted down near the circuit board, it's a good idea to have some insulation on there, even though it is going up on studs. But yeah, the instructions recommend putting a piece of electrical tape or even scotch tape over it. I have a lot of this mylar, so I'm just going to super glue some mylar down to it, insulate the whole back. And the battery holder is mounted with the 2 screws into the short standoffs. It doesn't really need the insulator because it is up on standoffs. I'm guessing that originally the instructions were written when the battery holder is just bolted down flat against the board, but it doesn't hurt to have the insulator on there anyway. And then the wires are cut short so they can go into the 2 holes in the circuit board there. I'll make sure I did the right ones. Yep, plus is the one towards the corner of the board. There's a set of jumper positions. One of them is up here, that's J5, and then J1 through 4 are down here. And the instructions just call for soldering a piece of wire between them, but I hate doing that. Then if you change something, you're constantly soldering and unsoldering. So I'm just going to put in some shunt pins and some shunt jumpers, if you will, or just shunts from my own part supply. Alright, all the jumpers have been put in there, and the shunts have been put in positions recommended by the manual. Most of them are open, so I'm just storing a jumper hanging off of 1 pin. But the 3 position one here needs to be in the left position, and the 2 position one on the bottom, that's J4, needs to be shorted with the shunt. Okay, and the last part to go on here is the stacking header, which is right there at the end of the IC socket. That provides a female on one side and a male on the other side for connecting USB adapter cables, such as this one that's furnished with the kit. This one here would need to go into the female on the top, and the jumper there might need to be moved to the back side. That jumper, which just comes with this adapter, the way it comes from whoever supplies it, is there to program it to use either 3.3 volts or 5 volts, but that's already taken care of on the circuit board, so this jumper does not need to be used and can be removed. And there are all 4 ICs plugged into their sockets. The batteries included with the kit are rechargeable types, nickel metal hydride, and there are 3 of them, and they go into the battery holder. There is the USB adapter plugged in to the badge, and the orientation of it is determined by the writing on the bottom, which has 5 volts on the left here and ground towards the right, and that corresponds to the markings for ground and plus 5 volts on the circuit board. Now, to use this for USB communications to this, between this and your computer, you'd need to get a driver and everything that matches this and install it on the computer, but simply to power this and charge the batteries from a USB power source, a driver is not required. Okay, I've just used a generic USB power supply and a USB-A extension cable to get to the adapter, and I've got display activity. It's random, of course. Just garbage on there, but it is working. So, no fundamental assembly errors, I think. Alright, I've let the batteries charge for a few hours. The badge runs whenever power is applied, whether it's from the battery or from the through the serial connector. So the power switch only applies to running off the batteries. So I'll turn the power switch on now. And indeed we do get the scrolling message, albeit one that's a little hard to see. So the next thing is to try programming it. Alright, the programming sequence is fairly simple, but will probably prove to be rather awkward. So pushing the set button, that's this red button over here, will freeze the display so it stops scrolling. The display is really just showing the contents of the 16-bit registers inside the 1802. That's the only RAM there is in this, and it's not technically RAM, but it can be used like RAM. And the program is written in such a way that it just uses those RAM locations or those register locations as RAM, and it's written so that it doesn't need to have any other RAM. So it can do all of its manipulations within the resources of the 1802 itself. You know, you can write it so any temporary values are in the D in the D register, or the accumulator as it's called on some other processors, and arrange it so all the reads and writes are from the are from the 16 registers, and then those are just sent out to the 2 chips here which handle the display. So anyway, so you push the set button and hold it, and that stops it scrolling and allows you to change whatever character it's currently on. If you turn the badge on with the set button currently pressed, then it automatically indexes to the very first character in the 32 character message string. And then you just use the up and down buttons to scroll through the available characters, which can be any alphabetic character, capital or lowercase, the digits 0 through 9, and some limited punctuation. I presume one of those is a blank, because there's clearly blanks in this message that's scrolling by. And then you briefly release the set button and push it again to index to the next character. And I'm not sure how brief that has to be, but I think that's the tricky part. Anyway, I'm going to try to put in a message that I figured out that'll be exactly 32 characters long. But I'm not going to show me stumbling my way through it. Okay, I've turned the badge off. I've pushed the set button and held it. Turned the badge back on. It is not scrolling, and the only digit that's visible, it's a little hard to see there, but it's the very rightmost digit. So apparently that's the very first digit in the string of 32 characters that the message is made up of. Okay, I've successfully programmed the first digit and then briefly released the set button and pressed it again, and it indeed has indexed to the next character position. The P that I put in as the first character has moved to the left, and now it's got whatever random thing is in the second character position, and I'm going to change that, and so on. Alright, I've got my message going there. Paul Schmidt, build of 1802 badge. Worked just like the instructions said, because you have to go around and around through the alphabet and the numbers and the punctuation and stuff. It was important to know which direction was shortest from whichever random character was there, so I actually mapped out the alphabet and what each character looked like. The uppercase is really clear. There's some of the lowercase that are like, what? At first, and then you can kind of see it. Followed by the numbers. And the number 1 you have to use a lowercase L. 5 you have to use an uppercase S. 0 you have to use an uppercase O. And there's a blank, and there's a period, and a forward slash, and a hyphen, and an @ symbol. Those are the punctuation. But that way I could say, oh yeah, it's much closer to go forward or backwards to get to the letter or character I want. So I mapped that out. And because you end up spending a lot of time holding this little button down while you're cycling through all the characters for each and every character in the message, my thumb was really hurting. So I soldered on a little, let's see if I can unzoom this here. I soldered a little shunt strip or pin header onto the back side pads of the set switch so I could clip onto it with something, and then I just got a little toggle switch from my junk box, hooked it up with mini clip leads, and put it in a pan of ice so I could easily sit here. Switch forward is run, switch down is hold or freeze. That made it so much easier. Anyway, it works. The only thing I haven't checked yet is programming the messages by serial connection to a computer. I'll be addressing that next. Alright, I have a Sparkfun FTDI adapter USB to 5-volt serial cable, which is snaking its way around. And because that is not the adapter that this kit was designed to have plugged into it, I had to make a little adapter to swap some of the connections around between the two plugs. And it is definitely powering the badge from that. And if I turn the power on, it shouldn't make any difference. So now it's not running off the batteries, it's running off of this for sure. And I see where my device manager on my computer says that COM3 is the one assigned to the FTDI serial converter, and that the device is working properly, so I know that COM3 is the one I should be looking at. And I have my tera term let me go in here. I've set it up for serial, but I have to go and change the COM port, their USB serial COM port. Okay. And I'm going to expand this to take up more of the screen. And unfortunately, I'm going to get all sorts of lights and stuff reflecting on this. It's unavoidable. I've pulled up TeraTerm's serial port setup dialog box, and according to the instructions with this badge kit, it should be 9600 baud, which it is. No parity, none. 8 data bits, that's what it is, and 1 stop bit, which is what it is. So it's already set up correctly. I'll save that. And I'll go back and look to make sure it's still the same thing. Okay, now the instructions say I have to turn the badge off, unplug the USB adapter from the badge if it was plugged in, so I have to do that. I have to hold the down button and then plug the USB adapter back on. The badge will automatically turn on, and I should see a set of 32 blanks framed with arrow brackets on the terminal. So I have to hold the down button and plug the cable in. Okay, that seems to be working. 1802 name tag version 0 by Lee Hart and David Madole. Tab to skip ahead, return to blank to end. Current message, Paul Schmidt, build of 1802 badge. So that's working perfectly. Okay, cursor keys don't work. And it does say on here, tab to skip ahead. So I'll try pushing, well, I'm just going to type in what I want. I have a new message made up. Okay, I've edited the first thing. Lee space capital H-A-R-T space designed space this space 1802 space, oh, I typed something wrong there, and I have to tab return to blank to end. Okay, that sent it back to the beginning. (1802). Oh, that's right. It doesn't know the number 1. That's the reason I'm having trouble with that. Go tab. I have to use a lowercase l. 18, and O has to be a capital O instead of a 0. There, that's okay. Space capital FTDI, because there isn't room to type more. Or maybe there is. I'll hit return again, tab forward, capital BADGE. Okay, so yeah, that's what I thought. I didn't realize it was putting an empty space between the carets. So I have to push return again, tab forward, and put in the shorter word that I was originally going to put in. Tag space. Okay. Lee Hart designed this 1802 tag. When you have entered the last character, hit Enter key to end. Unplug the USB adapter and turn the badge on. So I'm going to unplug this. And I'm going to turn the badge on. Lee Hart designed this 1802 tag. That works perfectly. Alright, we're cooking with gas. Alright, I redrew the original schematic that came in the manual for the 1802 badge. And I did that because it's the usual schematic that's done by software that's tied to circuit board layout software, and as such it's functional, but the layout is often compromised because those programs aren't very good CAD applications. They're just there to give you something you can put in so that the board layout software can do its auto routing and also check that you put all the connections in. So I've redrawn it in a more conventional way, tried to unclutter it a little bit and still fit it on a piece of note paper. So it's a classic circuit for the most part. We have our microprocessor here, the 1802. We have a octal latch because the 1802 sends out its 16-bit address on an 8-bit bus. So it has to send out, I can't remember which now, it sends out the upper byte and then the lower byte one after the other. And there are a couple of pins, TPA and TPB, that have to do with letting external circuitry know which half of the address is currently on the address bus of the chip. So we need an octal latch here, and this is keyed into latch in whatever's on the 1802's address port or address bus whenever TPA is on. And when TPA goes away, then you can change this data coming out of the 1802 and the latch will still remember what it was. So this is putting out the upper byte here, A8 through A15. So when TPA is on, that means that the 8 bits coming out of the processor are the upper half of the address word. And then the rest of the time these can be the lower half of the address word. So I've got them bundled together into this heavy line that represents the overall 16-bit address bus. And it's going to the EPROM chip, that's your ROM, and it's using most of the address, but it's only a 32K EPROM at its biggest. It's in this case a 27C256, which is the CMOS version of the standard 27256. That's again a 32K part, so that holds any program that there is. So we have A0 up through A12 directly off the bus, and then if we were using A13, we could put a jumper at position J1, and that would connect the bus's A13 through to the chip's A13. But with the jumper removed, this is just floating, and it'll float high. And it doesn't matter because there's no program in here that goes anywhere near that big. A14 can be configured by various jumpers. In the version for the name tag or the badge, this jumper J3 just ties this high, so it's a logic 1 all the time. So essentially A13 and A14 are at logic 1 all the time as far as anything here is concerned. And then finally A15 goes to the chip enable. So, but the chip enable is active when it's logic low, so only when A15 is at a logic 0 can the EPROM be active. And that's because in the overall 64K memory space of the 1802, the EPROM resides at the lower half of that, the lower 32K. So that's straightforward enough. And you have to be able to tell it whether or not you've got an EEPROM, in other words, an electrically erasable programmable random access memory, or read-only memory rather. So this is a pin that deals with the programming voltage if you did have an EEPROM in there. But this circuit can't program or provide that programming voltage, so by tying it to VCC, you're telling it that you're not trying to do any programming of the chip. And then finally the output enable is tied to the memory read signal on the 1802. So whenever you've got the appropriate address in the lower half of memory and you get a memory read command, it comes over here, turns on the outputs of the EPROM, and whatever's in that particular address space in the EPROM gets sent out the data bus, and it makes its way back down into the 8-bit port of the 1802 that's designated for use as the data bus. Likewise, there's a RAM chip. This is only an 8K RAM chip, but it could be a larger one. It's very much like the EPROM. Address A0 through A12 are directly tied to the address bus. A14 on the bus goes to the low, or the active low chip select 1 line of the RAM. In other words, A14 has to be at logic low for this chip to be active, and A15 on the bus goes to chip select 2, which is active high. So A14 has to be low and A15 has to be high in whatever address is on the bus at the moment in order for this RAM chip to work. Then, because it's RAM, you have to have a write enable and an output enable, which is a read enable. The write enable comes here from the memory write output of the 1802, and it's active low on both ends. And the output enable is also active low, and that comes from the memory read, also active low. So that's very straightforward and simple. But again, unless you're trying to do something fancier which hasn't yet been developed, either by Lee Hart and his friends, or as far as I know by anybody else who's built one of these, there's no RAM in the picture. It doesn't need RAM to operate. It's only if you decided to turn this into a more full-fledged microcomputer instead of just a name badge that you would actually put a RAM chip in here and do something with it. And of course, if you're going to make it run BASIC or some other utilities, you would have to have RAM in there because those programs are too complicated to do without lots of RAM, and of course you'd need to have a place to put your user program in. So that's how the RAM works. Just looking at some of the pins on the 1802, the 1802 has two power supply pins, VDD and VCC. The VCC is like the VCC on any logic chip. It's your basic 5-volt power. But on the 1802, it is mostly for things that take a lot of power, such as running the I/O signals, the bus, all that stuff, any other power-consuming functions. Where VDD keeps alive the core of the processor, especially the contents of all the registers, and of special importance in the name badge, all the characters for the message are stored in the 1802's internal 16-bit registers, of which there are 16. And since each character gets half of a 16-bit word, in other words 1 byte, that adds up to 32 bytes. And that's what's needed to store a 32-character message. You obviously don't want to have all that lost every time you turn off the power, so VDD is arranged to be on all the time, thereby keeping non-volatile the 1802's internal registers and what we'd call kind of a pseudo RAM in the form of those 16 registers of 16 bits each. So that's why they're separated here. Otherwise you might just have VDD and VCC tied together. There are functions in the 1802 which deal with direct memory access. In other words, outside of the normal functionality of the 1802 doing what it's doing with the address and data buses, there is a DMA mode where you can directly write into RAM without using the 1802, except that it still controls the address bus. So you can force data externally into the RAM without the 1802 getting in the way, and at the same time you can command the 1802 to sort of play back the contents of the RAM separately from whatever it's normally doing and make that accessible to the outside world. So you can essentially read into memory or write out of memory while the 1802 is still nominally doing its thing, but do it with external stuff. But we're not using those here on the badge, so they're both just tied to VCC, thereby disabling those two functions. There's also a couple more housekeeping pins, SC0 and SC1. Those are state codes. You can tell exactly what's going on in the processor by binary patterns on these 2 bits. We're not using them here, so they're not connected. There are also these 3 bits, N0 through N2, which are kind of like address pins for direct control of I/O. So you have the binary patterns possible with 8 bits, in other words, 8 I/O locations, and there are commands in there to, write into or read from the I/O that's at any of those 8 positions. So that's what this is about. We're not using those on here, so they're not connected. You can have either a crystal oscillator or an externally fed clock from other equipment, or a ceramic resonator. In this application, the resonator is used. That has essentially, the ceramic resonator is much like a crystal in this sense. It has a couple of built-in capacitors to ground, and to make it work properly you also have to put a high-value resistor across it. And in this case there are 2 1 megohm resistors. They're actually parts of a resistor network. So that's what's going on there, and that's what makes the processor run with its clock. Let's look at the I/O port, or the serial port. It's a 6-pin connector called P1. It's expecting 5 volts on pin 6, but that has to be jumpered to the VCC. If you're going to be operating the USB to serial adapter plugged into this plug, it's typically going to operate at either 3.3 volts or 5 volts. And by tying this pin to this pin, you can tell it how you want it to behave. Now the USB to serial interfaces that are typically used with things like this can be programmed externally, and indeed pins 5 and 6 are jumpered together on the badge's circuit board, so the device out here knows it should operate with 5-volt signals. And it's also a way of getting 5 volts out of this, supplied by the USB connection, to power the badge, and that's VCC. And there's ground, and there's a capacitor there just for a bit of filtering. There is a reset where you can command in a terminal emulator to send a particular serial command, and that's interpreted as a reset, and that goes through this resistor and a couple capacitors and a pull-up resistor to the 1802's clear input. That's active low, and even without anything connected here, this resistor and capacitor perform a power-up reset every time the power is turned on, because the capacitor will momentarily act as a short circuit until it charges up, and it charges up through this resistor. And while it's acting like a short circuit, it's pulling this low, and therefore it's going to tell the 1802 to reset. And again, you can send a external command to force it to do a reset through this connection here. Alright, there is serial I/O here, and as is usually done these days, all that's needed is a TXD or a TX and an RXD or RX. So data's going one direction and it's going the other direction, and both are handling serial data, just in opposite directions. They could be going on at the same time, actually. And the USB to serial adapter takes care of converting the USB protocols to basic serial protocols with these two signals. Because the adapter is expecting simple 0 to 5 volt logic on these pins, it's easy enough to take the Q output, which is the 1802's single bit programmable output for simple I/O things, and run that directly to the TXD. So this is the 1802's transmitted serial data coming out, and it's already 0 to 5 volts because it's coming directly out of the Q output. So there's no need to interface it any other way. The RXD, or the incoming serial, as a pull-up resistor, it's another part of the 1 meg resistor network, and that goes into two places. It goes into interrupt the 1802, so it can take action every time it sees a pulse here, and it also can be read directly by one of the 4 testable input pins on the 1802, EF1 through EF4. Those are just points that the program can interrogate to see if they're currently low or high and take appropriate action depending on which one they are, low or high. So you can interrupt here, and then the interrupt routine can look at EF3 and see whether the data is currently high or low. So a very simple and straightforward method of clocking in, or not clocking in, but reading in received serial data. And there is no UART functionality in the 1802, so it's bit banged. In other words, a fairly simple program can keep track of the incoming data, and through the use of the interrupt and the EF3, it knows there's data and it knows what the data is. That's making it maybe a little simpler than it really is, but it's good enough to give the general idea. Now there's 3 push buttons on the badge. There's a set button, there's a up button, and a down button, and each of those 3 are pulled up with a 5.6K resistor, all part of the same resistor network, and then they're applied to EF1, EF2, and EF4. And therefore the running program in the 1802 can be interrogating these to see if they're being pushed or not, and take appropriate action. Now let's look at the display. We have the data bus coming out of the 1802, and besides going elsewhere, it also goes directly into the 8 inputs of an octal buffer. This doesn't do any latching or storage, it just passes the data through or it doesn't, depending on the status of these two pins, output enable 1 and output enable 2. They both need to be logically low in order for the buffers, the 8 of them in here, to pass through from, it's called A8, that's got nothing to do with addressing, that's just what the chip calls it, A8 to Y8, that's the output, A1 to Y1, and etc. So when so commanded, this will take whatever's on the data bus and send it out here. Well, let's see, right off the bat, there's a jumper here, but there's no jumpers on it. It's a place for a jumper. It can be tied either to VCC, which would permanently disable this because it's expecting a low in order to do anything, or it could be tied to address line 15, or it could just be left open, in which case it's logically pulled high internally, which means it's not active. Let's see. So whenever the data is passed through, it appears here, and because this is a buffer, it has pretty good drive capability. It can sync and source more current than, say, the outputs of a normal logic chip. And we have the display, the LED display. It has 2 modules of 4 characters each, and they're what's called a starburst type instead of the regular 7 segment. So they have twice as many segments. And if you're familiar with regular 7 segment displays, the top one is called A, the top right is B, the lower right is C, the bottom one is D, the lower left is E, the upper left is F, and the center across is G, and then of course a decimal point. That's your normal 7 segment, but on here there's actually a short and a long upper segment and a long and a short lower segment, and they're called here A1 and A2 or D1 and D2. So they're keeping the same letter associations as a normal 7 segment display, and the middle one is G1 and G2 because it's in 2 pieces. And then we have H, which is lower or upper left to lower right, and it's in this case because it's not trying to follow the lettering of a normal 7 segment display. It wouldn't call it H1 and H2, it'll just say H and I, or it leaves out the letter I actually, so it's H, L, and then keeping with the clockwise theme of the 7 segments, the next digit you encounter is M, and then N, and the diagonals are J, so you see how that works. All told, there are 15 possible segments in there. These displays are common anode type, so for each digit there is the anode, so you can think of all these LEDs as pointing in this direction relative to these common pins. And this is considered digit 1, digit 2, digit 3, digit 4, and then the next bank of 4 is also 1, 2, 3, 4. So in order to turn on any segments in here, you have to turn on the appropriate cathodes up here applicable to the associated segments. You have to energize the common anode, and then whichever segments you want to turn on, you have to provide a path to ground from these pins, which are tied to the various segments. And these are common across the board, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 possible connections, and they all go directly to the address bus. The only one which is not used is A15. And the reason for that is, as we remember from up here, the RAM is in the upper half of memory when A15 is logically high, and the EPROM is in the lower half of memory when A15 is logically low. And as we're about to find out, this bank of LEDs is addressed into the same space within the lower half of memory as the EPROM is. So you'll have some address in the A0 through A15, or A14 rather, address lines, and whatever address is out there, not counting A15, those will be the logic zeros you need to have to turn on a particular segment. And then you only do that for one digit at a time. It's multiplexed. So let's say we want to operate this one. We program the data bus to buffer through a pattern that has only this bit on. That's Y1, that's D7. So the D7 on the data bus would be turned on. That'll cause Y1 here to turn on, thereby making the common anode positive. And then whenever the address bus has an address that corresponds to the bit pattern that we want on that one digit of the display, then those segments will turn on and make the desired pattern. And then we change to a different address that's maybe the bit or the segment pattern for this, and then we have the data bus turn on and give us the common anode to energize that one, and so on down there. So we're actually driving the intelligence of what we want to appear on the display off the address bus, not off the data bus as you might think. And that, I'm sure, also makes programming fairly simple within the 1802's instruction set. So there are some caveats. So whenever the 1802 is trying to write to RAM or write to EPROM, which of course the EPROM can't take, but remembering that the addresses also correspond to the display, so we're in that address space. We've arranged to have the address bus providing an address that's corresponding to the bit pattern we want on the display, and then we send out on the data bus the appropriate signal that will energize one and only one of the display digits. But the 1802 naturally, at least when it's running at 2 megahertz, the bus cycle is only 4 microseconds long. That's not enough to see anything on the LED. You'd never see it. It would turn on, but it'd be so brief that you wouldn't even notice it. So there needs to be a way to lengthen the amount of time that the address bus keeps the appropriate pattern on it, instead of going away 4 microseconds later. So whenever the 1802 is trying to write to the EPROM address space, which means it's really writing to the display, there's a little bit of RC logic in here that puts the processor into the wait state every time that write to the display happens. So we know that the RAM space is in the upper 32 kilobytes of memory space, and the EPROM is in the lower 32K. That means that the distinguishing address characteristic between those two banks of memory is that address line A15 is logically true or high for RAM access, and it's logically 0 or low for EPROM address, which is the same as display. So address line A15 comes down here, and it goes through a Schottky diode to this point. Now I'm going to digress and say every time that the processor is trying to do a memory write, in other words, writing to memory, this line here goes low. And here you have a capacitor with a resistor pull-up, and the middle of that is going to the wait input, which is active low. So it's normally being pulled up by this resistor, therefore the processor is not waiting. But when memory write goes low to allow memory like a RAM to accept whatever's on the data bus, when that goes low, because this capacitor temporarily acts like a short circuit, it can pull this point low against the pull-up resistor, therefore it puts it into a wait. Now the capacitor charges back up through this resistor, and once it charges up roughly half the power supply voltage, then it'll be treated as a logic high, and therefore the 1802 will no longer be in wait state, and normal operation resumes. So that's where you get that lengthening of the normal 4 microsecond bus cycle, lengthening it up to approximately 1 millisecond of duration, so that the LEDs are on for plenty of time to be seen easily. Now, we don't want to get that wait function for any old memory write, only when we're writing to EPROM space. So when address bit A15 is on, which means that the area being addressed is RAM space, this being logically true here goes through the Schottky diode and forces this point to be logically high. So even if the memory write pulse is low and the capacitor tries to pull this low, it can't because it's being forced high by A15 coming through the diode. So this little time delay and wait state is prevented from functioning whenever you're in the upper memory space or when the CPU is addressing RAM. There's another thing that happens with that. We also want to turn off the other half of the display, because remember that anything that's going on here on the data could feed through the LEDs, which are just diodes, and they're connected directly to the address bus. That could mess up what's on the address bus whenever you're doing other stuff. So you want to make sure that the outputs of this buffer are turned off whenever you're not trying to write to the display. So we have this output enable here, and it's connected up, and through the diode it goes to A15. So once again, if we're in A15 equals logic 1, then that disables the output enable here because this is active low, and it prevents the outputs from turning on. Therefore this is just like it's not connected, and as far as the address bus is concerned, these diodes aren't even here. And I should also clarify that this octal buffer is a tri-state output, so the output pins can either be logic 0 or logic 1, or the third state, which is open or very high impedance state. So the rest of the circuitry connected here sees it as being disconnected, and that's how you facilitate getting this electrically out of the picture whenever you are accessing the upper half of the memory, in other words RAM, that this chip is disabled, therefore the outputs are in tri-state mode, they're high impedance, and it's as if they're not even there, therefore these LEDs are not there as far as the address bus is concerned. So let's take a look at the power supply circuit. First off, we have a battery that's comprised of 3 cells. Each of them is a nickel metal hydride cell with a nominal voltage of 1.2 volts. So with 3 of them, that adds up to a nominal 3.6 volts. So lower than the 4.5 volts you would have if you had alkalines in here. Now what we want to do is whenever external power is being applied, we want that to recharge the battery. But when external power is not being applied, we want to discharge the battery in order to keep the badge functioning under battery power alone. So the rest of this circuit is what accomplishes those two things. Now the VCC here is the input to this circuit, and VCC is derived directly off the connector where the USB serial adapter plugs in. And because it's coming from USB, there's a built-in 5-volt power source, and that is where the VCC everywhere in this circuit comes from, including the power supply circuit. So we can just think of this point here as coming from the USB serial adapter. 5 volts coming in. There, I added it in. So let's say the power switch is off. So this is open. And you have a Schottky diode here. Now the Schottky diode spec sheet will say that it has a forward voltage of as high as 0.5 volts, which is pretty close to the 0.6 volts for a normal silicon diode. But as I was reminded after pondering this, the specifications usually call for worst case voltage drop, but in reality when you're using the Schottky diodes in low current situations, then their forward voltage drops quite a lot, and it may only be about 1/4 of a volt, 0.25 volts. So we come in here with 5 volts, we lose, say, 0.25 volts, so we have 4.75 volts over here, and that is connected through this resistor. It can't go through this diode because it's reverse biased. It goes through this resistor, which is a current limiter, and into the battery to recharge it. This can't have more than 3.6 volts on it, and this being 4.75 volts, it's going to push current through the resistor and into the battery, recharging it. And a nickel metal hydride cell or battery can be trickle charged indefinitely, so you don't need to do anything here to shut this off when the battery gets charged. It'll just continue to trickle charge it as long as the external power is applied. Now this point here, which is again 4.75 volts, that is the source of VDD, which is used by the 1802 to power its more critical internal functions and maintain whatever's in the registers. So that's a very important aspect of this design, that even with power removed, the battery is able to furnish the VDD to keep the CPU alive and not lose its memory, which has all your program message in it. Anyway, so then when you disconnect the external power, now the battery is the source, and instead of pushing current through this charging resistor, it bypasses that through the now forward biased Schottky diode here, and once again we get VDD from that. And let's say we've charged up to 3.6 volts and we lose about 0.25 volts through the Schottky diode, so you get that voltage here. And now if you're not turning the power switch on, that's as far as it goes. This diode is reverse biased, so the battery's only providing VDD to keep the CPU alive. But when you turn the power switch on, now you're also providing VCC from the battery, and both VCC and VDD are the same voltage when the power switch is closed. And if I didn't say so before, I'll say it again here. When you're powering the badge from the external power, it doesn't matter whether the power switch here is open or closed. Everything will work the same way because the power is going through this Schottky diode and bypassing the power switch altogether. and it will power the badge circuitry in addition to what I'd said about charging the battery. And I should clarify that even though the schematic says this can be a 32K EPROM, the part that's included with the kit in its basic name badge functionality is a 2764, not a 27256. Therefore, it's only an 8K EPROM, and that's obviously more than sufficient for the small amount of programming that needs to take place for this badge to work. So I want to talk about how the badge accommodates the storage of character data for 32 characters and still has some sort of RAM or internal storage left over to do whatever it needs to do for program execution. So we know there's 32 characters in a message, and there are 16 registers in the 1802 of 16 bits each. And that's really all we have that's like RAM in the badge circuit, even though it's not technically RAM, but you can treat it like RAM. So the reduced alphabet and number system that is available on the badge is the capital letters A through Z, that's 26 characters, lowercase a through Z, that's another 26 characters, the numerical digits 2 through 4, and that's because 1 is done by a lowercase l and 5 is done by a capital S. So 2 through 4 gets us 3 more characters, and then picking up after the 5 we have 6, 7, 8, 9, that's 4 more characters, and 0 is represented by a capital O. And then finally there are 5 punctuation characters. If you add all that up, it's 64 characters. So just keeping things simple, if you had 4 bits to hold characters, we know that in binary 4 bit positions, 4 positions of binary, in other words, can get you numbers 0 through 15, or 16 possibilities. If you add another bit and go from 4 bits to 5 bits, you double that and can go up to 32. If you add another bit, then you can go up to twice that, which is 64. So 6 bits will get you 64 characters. Now let's presume we have a bunch of 16-bit registers in the 1802. If we pack it in there, so for example, and I'm not sure this is exactly the way it's laid out, but let's pretend like there's 6 bits that represents 1 character, another 6 bits does another character. If we had a third 6 bits, that would be 18 bits, which is too many for 16-bit register, so we can only fit 4 bits in there. And then the next of the 16-bit registers has 6 and 6 again, and then 2 bits, which picks up the remaining 2 from here to make it 6 bits total. And then the third register has got 6 and 6 again, with another 4 like up here, and its extra 2 bits are getting done by this position. So we can see here that there's 1, 2, 3, 4, 5, 6, 7, 8 times 6 bits. So 8 characters have their codes stored in 3 registers. So you do that 3 more times, 8 characters each, and that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 registers of 16 bits each can store all the character data for a 32 character message. Well, there's still a few more registers left over. They're using 12 here, and there's still 13, 14, 15, and 16. So those remaining 4 registers are used as RAM for the program that's running the badge. whenever it needs to store something in RAM, it just uses those remaining registers. And it can't actually use all of them because the program counter must be in one of those registers. So that kills one of those right away. And if it's doing indexing, then another 16-bit register is used up as the index register. And you might use it up, and you might use up another one for doing subroutines, that type of thing. But the point is that there are resources in that group of 16 registers beyond what's needed to store all the character data to be able to use some of it as RAM for program execution purposes. The fellow whose name I'm just going to call David, and that's because I'm not sure how he pronounces his last name. I won't mangle it, I'll just call him David. He worked out a clever algorithm so he only needs 2 shifts per character. That equalizes the thinking time that the program is doing. It equalizes the thinking time to extract each character from the registers. The 1802 uses the remaining 4 registers for program execution. We've already talked about how the LED segments are driven by the address bus. All the bits except for the highest one, A15, are used. So that's 15 bits. And the LED digits are selected by the data bus, only 1 bit at a time turned on to affect a multiplexing of the display. So there's a little nuance here that we're using address bits A0 through A14. The A8 through A15, again we're not using A15 for the display, but A8 through A14 come out of the octal latch. And that provides a form of buffering, so there's more ability to drive, or in this case sync current from the display for those upper address lines. But the other ones, A0 through A7, those are coming directly out of the 1802, and they don't have as much drive capability as the octal latch does. That means that LED segments, which are driven by the microprocessor directly, have less drive and therefore potentially less brightness than segments which are operated by the buffered or latched and buffered outputs of this IC. So how to deal with that? Apparently David programmed it so the segments that are driven by the CPU are operated for twice as long to equalize the brightness. So he's made a little algorithm that keeps those segments on for longer than the segments that are being driven by the buffered IC here. So there's a little nuance in the programming that does that, so that to the human eye, even though the amount of current going through different segments is different, because of the duration of those, it comes out looking the same to the eye. I already talked about how EF1 through EF4 are used. 3 of them are just being used to read the 3 push buttons, and the remaining one is used for the RxD or read data signal coming in. So if the serial input detects a start bit, that would be from the interrupt. So the first time you get a bit after no data coming through and it's just a DC voltage, once it starts pulsing up and down, that's a start bit, and it's basically saying, wake up, real data's coming immediately. So the interrupt detects that sudden change from DC to a change of voltage, a transition, and then subsequently the program is now running a subroutine that was triggered by the interrupt, and that subroutine is reading the on and off data of the serial data stream through input EF3. And it'll do that until it's determined there's nothing else coming, and then it'll exit the subroutine and go back to normal operation. So actually, during that time when serial data is coming in, the processor is dedicated to working on that rather than updating the display. And so my understanding is that the display stops working during the time when serial data is coming in, but so small an amount of serial data is coming in, just when you're using the terminal emulator and you're trying to program in a new message, you push a key, you get a very short message that says, hey, the letter F was pushed, or the letter X was pushed, or whatever. That's just a few bits. It's over in a tiny amount of time, and then once that's over, then the processor's back to running its normal program, updating the display, and then, you know, a couple seconds later, the operator pushes another key, there's another burst of serial data, and temporarily, again for a blink of an eye, the display is put on pause, and it handles the incoming data. And I know that basic routines for reading and writing serial data can be accomplished in remarkably small programs. I'm not sure about this particular case, but I've read that programs of 15 or 16 bytes are actually adequate to read in serial data or to generate serial data. So very efficient programs are possible, and probably something of that order is being done whenever you are reading or writing serial data to the terminal that may be hooked up to the badge for programming purposes. The thing I'm not sure about is how some of those algorithms work. I can imagine how they work. So, for example, how is the actual scrolling of the display handled? I can picture how the processor's going to look in to a register and pull out the 6 bits necessary for a character code, and even if it has to assemble it out of 2 different registers, that's done in a couple of machine cycles, very short amount of time and small amount of resources. But the other manipulations that are necessary to scroll the display, I suppose it could just run a little algorithm that moves everything down and actually rotates the character data through the registers and is always treating it that way. Or it could be that the data stays exactly where it is in the registers, and just the algorithm that's reading it and putting together the commands to drive the display, that is kind of shuffling the cards in its head, if you will, rather than having them laid out in order in the register stack. So there's a few unknowns there, but I think you get a general idea what's going on with this, what must be going on in order for it to function. Alright, I've designed a little holder for the name badge. It's going to look roughly like this from the top, so it'll be a frame with a recess on the top into which the badge will sit, and it only sits down about the thickness of the circuit board in that slight recess. And the box is wider, or the frame is wider, and there's also a separator in it, which the left edge of the circuit board should sit right about in the middle of. And then there will be a panel with a hole for the toggle switch that's going to fit in right up next to the circuit board and over to the edge of the recessed area over here. And that'll be glued in. It'll be printed separately. And There will also be a blank version of the panel with no hole in it, in case somebody doesn't want to have the switch, or if they want to make their own and drill their own holes or something. It'll be just a little bit taller than the height of the badge. Allowing for the curve on the cables of my little jumper that'll go on there to wire out the set switch to the toggle switch. There will also be some little pads in the corners to act as feet, and they're sized to work with the commonly available little felt or rubber adhesive foot pads that can be purchased in hardware stores and so on, to stick onto those 4 locations and make it kind of like a grippy surface if it's sitting on a table. In addition, there will be a little piece to act as a spacer for the switch to slide over the bushing and have just enough room for the nut and the lock washer, so that you don't have a bunch of this sticking out above. It's nice to get it so it's more like that. So several pieces to make, none of them very complicated, and I'm going to be using Tinkercad. It's just the addition of simple geometric shapes in positive and negative space. To keep things simple, I'm just using a snap grid of 1 millimeter, and I've measured everything out in the design to be in millimeters. Although the circuit board itself is clearly in inches, I just made it slightly bigger to the next millimeter. And the same with the switch. The actual diameter is a 1/4 inch, and that doesn't translate directly to anything in millimeters. If I go to 7 millimeters, it'll be too sloppy. If I go to 6, it'll be just a hair too small. So I'm opting to go with 6, and then it can be opened up by running a drill through it as needed. And if somebody wants to put a different kind of switch in there, they can use the blank version of the insert panel and drill it to their heart's content. So I've started out with a solid 3D object, a box if you will, but a solid box of 112 millimeters wide, 89 millimeters front to rear, and 30 millimeters high. Then I'm going to make another box in negative space that's 106 millimeters wide, 83 millimeters front to rear, and 2 millimeters top. That'll be for the inlay, and I will merge that with this solid one. So there's the negative box, and on the solid one I just have to move the negative one up to the top and get it positioned correctly in the X and the Y dimensions, so it'll act as the recess. There I have my thin negative space that's shown somewhat darkened with an outline, and it's sitting centered on the X and the Y dimensions and flush with the top, so aligned top. And all I have to do is group those so they behave as one object going forward. Okay, those have been grouped, so now it looks like a single object. And we can see that there's the 2 millimeter recess all the way around the top of the object. Alright, I have created another box in negative space, and I just need to get that over to the left side. This will be sitting on the bottom, and it already is. We can tell that by rolling it around and looking at it there, that it's on the same work plane. And so the first thing I need to do is get it centered left, or aligned left, and then bring it over 6 millimeters. Alright, I brought the negative space box in and aligned it on the left and the front, and then nudged it 6 millimeters over to the right and 6 millimeters towards the rear, so it is centered. Although, if the dimensions worked out right, we can see that it's closer to the front than to the rear, and that's because the the recessed lip on this side is going to be 6 millimeters instead of 3, which it is everywhere else. So I believe that's correct. And now I have to go and do something similar and make another large negative space box over on the right. But before doing that, I grouped them so it becomes a single object. And I can see here how the recess is there, and I've got the rear lip and the left lip and the front lip just like I wanted. Okay, I've got my negative space box that's 70 wide, 74 front to rear, and 28 high. And once again, I need to scroll out a bit so I can see what I'm doing. And I'm going to select the box and left click the other object so that they're both there, and then I'm going to select group. Alright, there's the combined object. I can see that it has the lip all the way around it. That's the recessed area with the lip around the recessed area. And I can see I've got the big opening for the bottom of the badge and the opening where one or more switches can be put in next to it. And now I just have to create an STL of this and then move on to the next piece. So I've raised this entire object up by 2 millimeters so that it's floating above the work plane, and that's the height of the little feet I'm going to put on the bottom. So there's the little foot. I'm going to need 4 of them, but you can see where it's going to slide under there. So I need to duplicate these and put one in each corner. There are the 4 feet. It's just a simple Control-C, Control-V duplication. Well, thinking about it some more and looking at it here, I really don't want it to be like that. The projecting feet don't really look quite right. So I would really like to have those recessed into the body so that they still provide a nice wide area for the adhesive feet to adhere to, instead of just trying to have them overlap a corner. But now that these are grouped, I have to figure out a way to ungroup them and then bring them up into the body of the frame. I'm not sure if Tinkercad will let me do that or not. I have to find out. Yes, I just had to do ungroup, and each time I click the ungroup button, it would ungroup the most recently attached thing to the group. Then if I ungroup again, it releases the second most recently attached thing. So I ungrouped 4 times in a row thereby unattaching the 4 feet, but leaving everything else still attached as a group. Then I selected that. Remember, it was raised 2 millimeters off the work plane, and I just lowered it back down 2 millimeters so it's sitting on the work plane, thereby absorbing the 4 feet, as you can see, like that, and then regrouping them. So now I have the completed shape of the frame that I wanted. And I'll just create the STL file so that I can print it. Alright, I've created a box that's 30 wide and 83 from front to rear and 2 millimeters tall. That'll be the blank panel that can go into the frame next to the badge. And I just want to check my dimensions here. So I hover the mouse over there. It is in fact 30 wide and 83 front to rear. And let's see, this is the one. Yeah, 2 tall. So all I need to do is create the STL file of this and make a copy of it, and then make the one that has the hole for the switch. Alright, I've created another project and copied and pasted in the panel from the previous small project, and now all I have to do is add a hole to it for the switch. And I'm going to do that by dragging a negative space cylinder into the project. And this is going to have a, since it's a cylinder, it's just, yeah, this can be made into an ellipse, so I have to be careful to put in the same dimension for each of these. And then set it to the thickness of the panel, which is 2. And there I've got my little negative space slug. And now all I have to do is position it the way I want it within the panel. So there is the negative space cylinder in there. And I can go over and look at it pretty much vertically. There we go. And select that object, and it needs to be 10 millimeters over to the right. And if because I'm on a 1 millimeter grid, if I tap the right cursor key 10 times, that'll move it over. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And it has to be back 25. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Okay, so there's that. And now all I have to do is group those. And now it appears with the hole just like I wanted it to be. Now for the switch spacer, I just need to grab a solid cylinder in here and set its dimensions. I was going to make this 12 millimeters by 12 millimeters, and the height is 4 millimeters. So there's that. And now I got to drag a negative space cylinder in and change its dimensions to 6 by 6 by 4. And all I have have to do is align those to the centers and group them. Get rid of this color. I don't much like the orange. What if it's magenta? That's nice. There we go. So there's my little switch spacer. And all I have to do is export that as a STL file, and the work is done. So I've created the holder, the blank panel, the switch panel, and the switch spacer STL files. I've got my Prusa slicer open, and with my directory here, I'm going to drag in the biggest thing first. That's the holder. Drop it there, and I can move it around. I'll put it sort of about there. The other parts are really small by comparison. So I'm going to print both the blank and the switch panel, so I'll bring in the blank. I'm going to move this over a bit more, so there's plenty of room for these. Right next to each other. And finally, the spacer. It always likes putting them right in the middle. There we go. All the pieces are set up for one printing job. And I can go around and make sure they don't look like they're in ridiculous positions. I'm actually going to move this one over a little bit. Move this one backwards. Move this guy up pretty close. Just minimizing the amount of traveling the robot has to go through when printing. Keep them fairly close together. My Prusa printer's got a good start on this. It's already starting the infill after doing the skin layers, and that's more apparent on the two panels there, the one with the hole and the one without. It's clearly got the infill going on with the squigglies. In other words, it's not filling the whole space with solid plastic. And our little spacer's already got a good start. It'll get up to 4 millimeters, then it'll stop printing that, and the two panels here will be done once they get to 2 millimeters thick. So it won't be that long before the printer's done with the 3 smaller parts and concentrates on building up the main holder. One last thing I had to do was go back and put the feed-through hole in the partition there. I'd forgotten that before I sent the job to the printer. That's okay. For this prototype I can just drill a hole, but for the ones I'm going to put up on my Fileshare website, it should have the hole in there properly, so I've added it. I've also created a version of the switch plate with text on it saying run and program. So there will be options. I just put some text in there, made it negative space, and recessed it down to the surface or below the surface, but not all the way through, only about halfway through. It's a 2 millimeter thick plate, so the text goes 1 millimeter in. Alright, 7 hours and 32 minutes-ish later, it's nearly done. Seconds away, I think. And there we are. The only things that I didn't get right, I'm hoping, is that I forgot to put the hole in there, and that I should have made this one with the embedded text in it. I forgot to do that. So I'm going to run another one of these with the text added. But yeah, otherwise, so far it's looking good. We'll see how everything fits. Okay, the badge fits in there just precisely. And I can put in the filler panel, which goes in there perfectly. Or I can put in the panel for the switch. And I have tested it, and in fact the switch bushing is just slightly bigger than the hole, so it will need to be opened up just a little bit, just a hair, to fit properly. But that seems to be about as good as I could have hoped for. Take a look at the bottom of it. It does want to sit up just a little bit here, and the reason for that is the battery cable there is really close to the edge, and I knew that was the case, but I figured I would just go in there with a file and take a little bit of the lip off there so that it drops down in at that corner. The rest of it's fitting perfectly. So I need to make a hole down on the side here. I can go in with a drill at a bit of an angle and make the hole. So that'll be fine. And I do have the little flat spots with a square cross section, or not a cross section, but a square area for the feet to go on. So, success. Alright, there's the difference between printing top up and top down, or face up and face down. This is the way it's designed, but the way it gets printed, it leaves borders and all that stuff on it. But if you do it with this side facing the printing plate, it comes out a lot nicer. Yeah, that'll be pretty nice once I get the switch installed and so on. Okay, so there's the switch mounted on the switch plate. The spacer worked out just fine. This particular switch has the more decorative nut on it, but some switches of this type will just have a regular hex nut. Anyway, it spaced it out appropriately, and the text looks good. So push the lever forward to run normally, pull it back for programming, which is the equivalent of pushing the set button. And I have my short length of cable going to a female header, which will plug into the pin header I soldered on the back side of the circuit board, connected to the pins for the set switch. And on the frame, I did just file away a little bit of plastic right there to clear this point here where the battery wires come closer to the edge of the board. and I drilled a 9mm hole in there to give plenty of room for this connector to fit through. I've put 6 little spots of super glue on the corners and the center sides. I have my 4 little translucent rubbery plastic adhesive feet. And okay, those feet are now stuck on. You can see the reason why. I wanted to put a little plastic there in the corner so the feet wouldn't overhang empty space. And now I can feed that cable through. Like that. Alright, there's how it goes together. The only thing I'm still waiting for is the green plastic filter for that. It's supposed to come today, but I got a notification that it's coming tomorrow, so I'll have to delay finishing this video until I can put that on and show how it works. So with those rubber feet, this doesn't move around, and I can easily throw this switch for programming. Okay, turn it on. And I can freeze it. I can change the character up or down. And single toggle it. To move through the message 1 digit at a time. And then resume for normal operation. Alright, I finally got my DigiKey order with the green filter material. It's from PRD Plastics. I think that stands for Proud. I think it's the guy's name, but I'm not positive of that. There's the part number and DigiKey's part number. I think I bought, because they're so cheap, I think I bought like 10 of them. For all the green LED displays I use, this should last more than a lifetime. Okay, here's how it looks with the green filter. Definitely an improvement of the unfiltered display.